There you go. And then a little bit of basic hydrogen peroxide, and you will get the desired alcohol. Just like that. Now, what if you want to put the alcohol on a double bond on the anti-Markovnikov carbon, the least substituted carbon? Well, to do that, you would just use hydroboration, oxidation. And this is a generic reaction, just so you can follow along with what I'm saying. We'll do mechanism here in a minute. But this is a generic way it's done. Take double bond, BH3. I put BH4 there. Should be BH3, pardon me. Not BH4, BH3. Borane. And that will add itself across the double bond, and you'll get the borane species. A little bit of basic peroxide, and you'll end up with the alcohol species. And that's the generic hydroboration oxidation reaction. Let's look at the mechanism. So now let's examine the mechanism of the hydroboration reaction. Let's take the two materials and let's examine them closely. Well, I think it's no stretch of the imagination that boron is the electrophile. It only has 6 electrons, wants to have an octet, so that's probably your electrophile. That means the double bond, the pi bond, is your nucleophile. But now we have to determine where is the most nucleophilic carbon. Is the most nucleophilic carbon here or here? And to do that, it's just resonance, right? So let's take a look down here. I could draw the bond up there. I'm just resonating the double bond. That's all I'm doing. Anion on the most substituted, cation on the least. Or we could have drawn it the other way, right? We could have also said cation up here, anion down there. So this resonance form and this resonance form, there's 3 of them. There's these 3 resonance forms that we need to think about. I think everyone will agree that this is the better one. It puts the cation on the tertiary carbon, the anion on the secondary carbon. So if we were to draw the hybrid structure of this particular alkene, we'd have to draw this. Delta positive there, delta negative is there. That means there's more electron density here, so that means the boron is going to want to attach itself here because this is the most nucleophilic carbon. So that means when this boron approaches this molecule, it will approach it with the boron closer to here and the hydrogens closer to there. So let's draw that. So here we go. As we've already seen, delta negative, delta positive. So the boron will come, placing the boron closer to the delta negative. That will happen, and then at the same time as the pi bond attacks the boron hydrogen bond transfers to the carbon. And this is done in a syn, S-Y-N fashion, which means the boron and the hydride will be on the same side. Plus the enantiomer. So here I have the boron coming in from the bottom. I drew it with the dashes, right? It could have easily come in from the top. It could have easily come in from the top and given me the wedges instead of the dashes. But I'm only going to draw one for simplicity's sake. So now, after this has occurred, we add basic peroxide. What happens in this reaction is, first of all, we deprotonate the peroxide. That's the first thing that happens. And the deprotonated base now will attack the boron. Something like that. And that will rearrange to put the alcohol where the boron was. A mechanism you don't have to understand. There you go. Something like that. Okay, so that's the mechanism of hydroboration oxidation. The key take-home message here is that the hydrogen and the boron add in a syn fashion, which will end up putting the alcohol and the hydrogen that you're adding on the same side. They'll also be syn. Now let's take a look at another example of hydroboration oxidation. That's a very similar example. Oops, not BH4, BH3. Now let's take a peek at the mechanism. And there we go. So now remember, this is going to be a syn addition. And one thing I haven't touched yet is that there's 3 hydrogens on this boron. So in general, technically, in actuality, it can do this reaction 3 different times. What actually happens is it actually adds 3 alkyl groups to the boron, and then you go through all the mechanism. But it gets a little cluttered, so I just do it once. And I just want you to know that it happens 3 times. So this reaction I'm drawing here, this mechanism, will happen 2 more times. But it gets really cluttered, really messy, so a lot of times I just leave it out. A lot of books just say multiply by 3 to indicate it happens a couple more times. So at this point, it could do it twice more, but let's just not worry about that because it gets really cluttered really fast. So here's my peroxide. Here's the base. Base deprotonates the peroxide. You get the anion, which attacks the boron. Which will give you which will rearrange to give you the alcohol in that position. Now remember, the alcohol will always be on the same side as the hydrogen you're adding because of the syn addition here. So the hydrogen and the boron were on the same face. So here the alcohol ended up on the same face as the hydrogen that was added. All right, so that's the example.